Okay, for number 6, they're asking us to find the asymptotes and holes, if any, in this rational function. Even though it asks for it first, we need to talk about, it asks for it last, we need to talk about holes first. And in order to find any holes, we need to factor the top and bottom of this rational function that we've been given. So up top, we do have a greatest common factor of 5x. When I pull out 5x, what's left behind is x squared minus 25. On the bottom, that is a trinomial that can be factored. We are looking for factors of 35, two numbers that multiply to positive 35 but add to negative 12. So that would be minus 7 and minus 5. We're not done yet. The top factors again. That is the difference of two squares on the top. And when we have it fully factored, that's when we can see that this function does have a hole. A hole happens at any factor that is common to the top and the bottom of our function. So we set that common factor equal to 0, and that tells us the hole occurs at x equals 5. But a hole is a point, so we need not only an x value, but also a y value. To find the y value, we're going to cancel that common factor, use the reduced function, and plug 5 into that function. So we get 5 times 5 out front is 25. 5 plus 5 in the parentheses is 10. And 5 minus 7 is negative 2. 25 times 10 is 250. Divided by 2, that does simplify to negative 125. So our hole happens at the point 5, negative 125. Now, for the rest of the problem, we do want to use this reduced version of the function. We're not going to go back to the original. We just use the original to find the hole, we reduce, and use that for everything else. So next up, we want to find our vertical asymptotes. And vertical asymptotes occur where the denominator is equal to 0. So we do have one vertical asymptote at x equals 7. We want to make sure that we write that as the equation of a line. The vertical asymptote is not 7, it's x equals 7. Then we want to consider our horizontal asymptotes and oblique asymptotes. We figure those out together because both are based on the degree of the numerator, the highest exponent, and the degree of the denominator, the highest exponent. For the degree of the numerator, you either need to distribute and multiply that back out or just kind of see it in your head. I'll go ahead and write it up here just so we have it. If we were to distribute that back, we would have 5x squared plus 25x over x minus 7. The degree of the top, that means, is 2 because of that x squared. The degree of the bottom is because we just have x to the first power. When the top is bigger than the bottom, that means we have no horizontal asymptote, and we do have an oblique asymptote, and we need to perform this division to figure out what that is. You can do that by synthetic division or by long division, whichever you prefer. X minus 7 goes on the outside, and we divide that into 5x squared plus 25x. So what do I have to multiply x by to turn it into 5x squared? I need a 5 for the coefficient and one more x. And then I distribute this down. I multiply by both terms. So I get 5x squared minus 35x. Then we subtract. So if we subtract here, if we subtract the negative 35, that becomes plus 35. The first column, if we've done everything correctly, should always zero out. And here we get 25 plus 35, which is what, 60x? We don't have anything left to bring down. You can bring down a 0 if you like it for a placeholder. What do I multiply x by to turn it into 60x? Well, that is a positive 60 is what I need. Multiply that down, distribute it. 60 times x is 60x. 60 times negative 7 is negative 420. Again, subtract. So this one is minus the 60, minus a negative. This one becomes plus. And there is our remainder, which actually doesn't even matter because this is what we're interested in. The equation of our oblique or slant asymptote is y equals 5x plus 60. This one doesn't ask us to graph, so that's it. We're done. Okay, number 7. This time we are going to go ahead and graph it. We're doing the whole thing. We're going to check for holes, asymptotes, intercepts, and then we are going to sketch the graph. And we'll take it from there. Holes, I can look at this one pretty quickly and see there is no common factor to the top and the bottom. The bottom does factor. It factors into x minus 2 and x plus 2, but neither of those factors also occur on the top. So no holes. Then we move on to asymptotes. Vertical asymptote happens where the denominator equals 0. So this one is going to have two vertical asymptotes. First one is x equals 2 from that first factor, and then x equals negative 2 from that second factor. Next up, we will look at horizontal and oblique asymptotes. Horizontal asymptotes and oblique asymptotes. We look at those together, and we look at the degree of the numerator. Notice our numerator doesn't have a variable, so that is degree 0. No x's up there. The bottom, maybe easier to see it on the unfactored form on our original, is x squared, so that is degree 2. When the top is smaller than the bottom, we automatically need to know that that gives us a horizontal asymptote at y equals 0 and no oblique. You can only have a horizontal or an oblique, not both. Next up, intercepts. Okay, I like to do y-intercepts first because they're usually easier. For our y-intercept, we're going to plug 0 in for x. So 3 over 0 squared minus 4. That is negative 3/4. So we do have a y-intercept at the point 0, negative 3/4. Oh, my pen has stopped changing color. Okay, it's all blue for the rest. X-intercept, that's when we take our function and set it equal to 0 because 0 goes in place of y, and we solve for x. When I multiply both sides by x squared minus 4, I get 0 equals 3, which is a contradiction. That's not true. So that means there is no x-intercept. And that's often the case when we have that y equals 0 asymptote. So now let's plot what we have. Again, my colors aren't going. That's so sad. Can I change it this way? Oh, there we go. So we have vertical asymptotes at negative 2 and positive 2. Horizontal asymptote at 0. You always want to dash in all your asymptotes. I like to do those first because they kind of help me with the rest of the problem. They kind of work as guides for me for what I'm going to draw for the rest of the problem. Then I go ahead and plot any intercepts that I have, any points that I already know. I only have one, 0 and negative 3/4, which is about here. Okay, and from there, I'm going to need a t-table to figure out some more points. Okay, so I'm going to start here in this middle section. Since I already have that y-intercept, I want to know what's happening when x equals 1 and negative 1. And let's use that table button on our calculator. I love that button. If we put in our function, which was 3 over x squared minus 4, and I'm going to go down to ask and okay. And then I can just type in numbers here. And look, they're already here. If I plug in +1 and -1, either one gives me a -1 for an answer. It just saves me some calculations. That's why I like to do that. So +1, -1, and -1, -1. And that makes a nice little parabola shape here. Remember that those asymptotes work as guides. So that kind of helps us figure out what's happening next in our graph. Then we are not done. We need to figure out what's going on over here. So how about some x values that are greater than 2? Okay, we already have an asymptote at 2, so maybe 3 and 4 and 5. And again, if you use that table button, we already have our function typed in there. You can get those results really quickly. If you like to have a decimal, because I think the decimals are sometimes easier to graph, you can go over to that fraction and hit your double arrow. So when x equals 3, y is 0.6. And when x equals 4, y is 1/4 or 0.25. And when x is 1/7, when x is 5, I was reading ahead, y is 1/7, which is 0.14. I'm just going to put 0.1 because we can't graph anything so specific anyway. So 3, 0.6, 4, 0.25, 5, 0.1. I mean, those are tiny decimals, but you can see what's happening. It's getting closer and closer to that asymptote. And then over here, we really have no choice. It's going to turn and go, oh, not away like that. It's going to turn and go up and get closer and closer to that vertical asymptote. Again, not done yet. We need x values over here on this side now. Okay, so now we need to fill in a little more on our t-table. How about -3, -4, and -5? And again, I still have that function in here plugged in, so I can just type in -3. Oops. -3, 4, and I'm out of order, but that's okay. -5. You can see we actually got the same values, same y values that we did for the positives. That's because of that x squared in there. So we get kind of a mirror image going on over here. -3, 0.6, -4.25, -5.1. Again, closer and closer, and it's going to follow that vertical asymptote up. Pretend like I didn't touch the vertical asymptote there. There we go. So there's our graph. Number 8, same directions, just a different function, holes, asymptotes, intercepts. So again, I'm going to start with factoring because I have to figure out if there's any holes. So there is a GCF, 3x, and then x minus 2 is left behind. The bottom factors into x plus 2 and x minus 2. And then we can see, yep, we do have a hole. Our hole is going to be wherever that common factor is equal to 0. So our hole is at x equals 2. A hole has x value and a y value. To find the y value, you reduce. So we're going to cancel these common factors, and we're going to use this for everything else, including the y value of our hole. So if we plug in x equals 2, we get 3 times 2, which is 6 on the top, 2 plus 2, which is 4 on the bottom. We always want to reduce fractions when we can, so that's 3/2. So our hole happens at the point 2, 3/2. Next up, vertical asymptotes. Again, use the reduced form. So we're going to take that denominator, x plus 2, and set it equal to 0. We have a vertical asymptote at -2. Horizontal asymptotes and oblique asymptotes are based on the degree of our function. Again, looking at the reduced function, we have 3x on the top, so that's x to the first power, degree 1. We have x plus 2 on the bottom. Again, that x is just raised to the first power. When we have a matching degree on the top and the bottom, that's when instead of looking at the exponents of our leading term, we look at the coefficient of our leading term. So we end up with here 3/1, the coefficients. So we have a horizontal asymptote at y equals 3, and that means no oblique asymptote. One or the other, not both. So we have a horizontal asymptote at y equals 3. Next up, we will look at our intercepts. Y-intercepts happen when x equals 0. So we have 3 times 0 on the top and 0 plus 2 on the bottom. 3 times 0 is 0, and 0 plus 2 is 2. 0 divided by 2 is 0. Some people get a little confused with that 0 in there. Make sure, if you don't know, do the work on your calculator. And then our x-intercepts happen when we set our function equal to 0, y equals 0. Multiply both sides by x plus 2. On the left, x plus 2 times 0 is still 0. On the right, we get canceling. Divide both sides by 3, and we get x equals 0. So that is also our x-intercept. When 0, 0 is one of your points, it is both a y-intercept and an x-intercept. So let's start graphing. Start with your asymptotes. Vertical asymptote at x equals -2. Horizontal asymptote at y equals +3. And then move to your Intercepts, we just have one right there at 0, 0. So that means, again, we need a t-table to finish things out. Again, I'm going to use that table button on my, well, I won't this time. In case you don't have a table button, I'll do it by hand so you can see. Okay, so we need to figure out two things. We need to figure out what's happening over here on this side of our graph. We already have x equals 0. So how about x equals -1 and +1? That'll tell us what's happening on either side of that intercept that we already have. So if x equals -1, again, I'm going to use that reduce function, 3 times -1 over -1 plus 2. That's -3 over 1 or -3. So you don't need the table button. You can do it by hand. Our next point. +1, 3 times 1 over 1 plus 2. That's 3 over 3 or 1. Connect the 3 points you have with a curve and then go towards your asymptotes. Don't stop there. You're not done. That's only half of the graph. We also need to know what's happening on this side of our vertical asymptote. So we need to pick some x values over there. So how about, let's see, the asymptote is at, I'm trying to get, sorry, thicker pen. Asymptote's at -2, so maybe -3, -4, -5, okay? Again, do those by hand, do them with your calculator, however you like. I won't use the table button, I'll just use my calculator in case you want to do it this way. 3 times -3 on the top, and -3 plus 2 on the bottom. Gives me 9. -4. I can go in and I can hit enter and pull that down and just edit it. So change the -3 to a -4. And we get 6. And then do the same thing with -5. And hit enter. There we go. Let's plot those points. -3, 9. -4, 6. And -5, 5. Connect those points with a smooth curve and then use your asymptotes as your guides. And there's our graph for number 8. Okay, number 9, we are moving into exponential equations. We want to solve this equation. When we have an exponential expression on each side of the equation, like we have here, if we had matching bases, if these were the same numbers, we could just take the exponents and set them equal to each other. They are not the same numbers, but they are related to the same bases, matching bases, okay? We can do a little trial and error in our head, kind of see what's going on there. I happen to remember that 4 squared is equal to 16, okay? Now, what is 4 cubed? If you don't know it, grab your calculator and do it. This is just kind of trial and error. We're experimenting here. So 4 to the 3rd power is 64. Oh, yay. Now I can do a little swap. Instead of 64 right here, I'm going to put 4 cubed. And then you need to keep that original exponent, 3x plus 2, because we just replaced the 64. And in place of 16, I'm going to put 4 squared and keep that original exponent. Now we do have a single exponential on each side with matching bases, yay. So we can just grab those exponents and set them equal to each other. We need to remember that when we have stacked exponents like this, they are multiplied together. So we'll end up distributing once we write out our equation. So to distribute on the left, we get 9x plus 6. Distribute on the right, 2x minus 4. I'm going to subtract that 2x. And how about at the same time I subtract the 6? So when I do that, 9x minus 2x is 7x. The 6 is 0 out. The 2x is 0 out, equals -10. Divide by 7. And there is our answer. It can't be reduced, so we'll just leave it like that. X equals -10 over 7. Okay, I had to pause the recording because I see that my answer is not right. And did you guys see it from the beginning right away? Yes, I copied this wrong. Okay. So my work is right if this would have been the right problem, but it's not. This should have been -1 here, which would have been a -1 here, which would have been a -2 here. So I would have added -2, -6 would make this an 8, which would make this 8/7, and that's -8/7. That's the answer on the answer key. That's correct. I just had a little copy error there. Sorry about that. Okay, number 10. How much money should we invest today in order to have $10,000 in 20 years if the rate is 4.5% compounded monthly? So this is an interest problem, compound interest. Specifically, the first thing we want to look at is what kind of compounding do we have going on here? Compounded monthly means we need to use this formula. And specifically, we use this formula with n equals 12 because the word monthly means our interest goes in every month, and n is always the number of compounding periods in a year. 12 months in a year means n is 12 for monthly. The other thing we need to read carefully on this one is on some of these problems, they're going to tell us how much we start with, and we calculate the ending amount. On other problems, they're going to tell us how much we end with, and we calculate the starting amount. So always read carefully to see which situation you are in. Notice this says how much money should be invested today. So we are calculating P. We don't know how much we start with. In order to have 10,000, so 10,000 goes in for A. In 20 years, if the rate is 4.5% interest, so 4.5% is 0.045, always change that to decimal. N, we already said, was 12. And so our exponent is going to be 12 times 20 for 20 years. Solving for P, notice that we have P times this entire expression here, which you can do that on your calculator. That's just a number. So if you have P times something and you want to solve for P, that means we're going to divide both sides by that entire expression. Because on the right, those two big pieces cancel, and we're left behind with just P. And then this is something, if you have especially if you have the multi-view, you can type this right into your calculator as is. You can simplify it and kind of do it step by step, but if you do that, you need to make sure you keep many decimal places until the end. You don't want to round anything until your final step. And if you do some intermediate calculations and you don't keep enough decimal places, your answer will be off by just a little bit. So I'm going to go ahead and just type it in exactly, oops, how I have it on my page. 0.045 over 12 or divided by 12. That's two different ways to do a fraction, works either way. And that whole thing is raised to the power of 12 times 20. If you don't have the multi-view calculator, you will likely need parentheses around those exponents right here, right there. You want to make sure the 12 times the 20 all goes into the exponent together. When I hit enter, there's my answer. Did this one give rounding directions? It didn't actually give me any rounding directions, but I will tell you when we're talking about money, if it doesn't say, we do want to do two decimal places because dollars and cents. So it would be $4,072.55 because we would round that to the nearest penny. After the 4 comes to 6 means we need to round up. So $4,072.55 is what we need to start with to end up with our $10,000.